the source sheet that we developed previously can be a little bit complicated to compute. The integral is rather simple, but we need a strength of lambda, and that at every point we have to recompute r and the r vector and integrate ds over the length of the sheet. And anyway, so this is often done numerically if we need to have actual some kind of complicated source sheet. But one way to simplify this is to look at a source panel. And so in essence, we can replicate a source sheet by putting in a number of panels where these panels are just straight lines, and then the strength along that panel can vary. It can be a constant strength or change linearly. And anyway, by increasing the number of panels, and in essence refining the grid, so to speak, we can closely approximate the continuous source sheet. So let's look at just a single source panel here. So we're going to put it on the x-axis. We'll say this is x, and this is y, and we're going to put a source panel along the x-axis, and this is a continuous sheet of sources that are collinear here. They all lie directly on this line. Okay, and then we can look at some point here. We'll call that P of x, y, and then we're going to have we're going to integrate just like we did above. We're going to integrate along this sheet, and this differential segment here, we're going to call that dx naught, just so that it doesn't get confused with this x up here. So we'll use x naught as the variable of integration, and so we're looking at some point here that's x naught comma y, and we're going to integrate then along the length of this panel. And what we'll get is that Vx, and I won't work through this math, but you can plug this into the equations above and make those simplifications. And the velocity in the x direction at that point in space is 1 over 2 pi, and we're integrating from x naught equals 0 up to L. And so we got x minus x naught lambda at x naught divided by x minus x naught squared plus y squared, and we are integrating over x naught. Okay, and then the y velocity is going to be y over 2 pi, the integral from x naught equals 0 up to L, where L is the length of the panel. So that's the length of the panel there. Lambda of x naught over x minus x naught squared plus y squared dx naught. Okay, so we integrate both of those equations over x naught from 0 to L, and that will give us the velocity in the x direction and the velocity in the y direction. Now we can actually simplify this further if we assume some distribution for lambda, or the strength of that source sheet. And so now there's a few different things that you can do. One of those, you can assume that lambda is constant across that source sheet. So this doesn't vary with x naught, in which case you can bring it out front. and then we simply integrate the rest of this inside the integrand. In our case, we're going to assume that lambda varies linearly. So lambda varies linearly. And so we're going to have, at one end, we're going to have lambda 1, and at the other end, we'll have lambda 2, and we'll say that it's a linear variation from that, or across that panel. And so that gives us that lambda of x naught is equal to lambda 1 minus x naught over L times lambda 1 minus lambda 2. Okay, so that's just a linear function that tells us the strength at any point lambda of x naught. So now we can plug that into these equations here for lambda of x naught, and we can come out and integrate that, and that will give us this final solution here for a and again, this is just for a panel that varies linearly, or where the strength varies linearly. So what we'll get is 1 over 2 pi L times, let's see, we're going to get minus y capital phi plus, that's a capital phi, there we go, plus L minus x capital psi plus L, and then so I'm writing this in a matrix form, so it simplifies it just slightly. Get L minus x capital phi plus y capital psi. Okay, and then over here we have y capital psi, or phi, plus x capital psi minus L, and bottom right we have x capital phi minus y psi. Okay, and then this is all multiplied by lambda 1 and lambda 2. Okay, so this is just a linear algebra way of looking at this, where we can now get the velocity in the x direction and the y direction. It's this matrix that we've got here in the middle times lambda 1 and lambda 2. So it just scales by the strength there, lambda 1 and lambda 2. And we need to define this capital phi, which is equal to a tan 2. So it's the arctangent, but we need to preserve our quadrant because the solution depends on whether or not you're above or below this sheet. And so anyway, we need to preserve the quadrant. So we're going to use a tan 2 of y times L, comma, y squared plus x squared minus xl. And then capital psi is defined as 1/2 natural log of x squared plus y squared over x minus L squared plus y squared. Okay, so given any point, any p, x, y, we can now plug that in for the x and the y's, down here, and get a phi and a psi, and then we'll plug those up into this matrix here. And if we know the strength lambda 1 and lambda 2, the velocities here, Vx and Vy, are directly proportional to those two, and the proportionality constant is this matrix out front with this constant 1 over 2 pi L out front there. So this gives us now the equation for the velocity induced by this source panel on any point in space, p, x, y, as long as that source panel varies linearly from lambda 1 to lambda 2.